Hello, everyone. I wish I could be there today, but I am ill. Got a positive COVID test, so that's a lot of fun. I hope to be better and back on Tuesday, but we'll see how things go. So you get video me today. So make sure you listen, pay attention, do what I say, and be good for the sub, please. I think you know who I'm talking to. Let's begin. You should have your study guides out. Let me share my screen so we can talk about what we're doing today. Let's see. Hopefully you can see this. We're going to do an activity where we build our own periodic table, and then we're going to look at an overview of different aspects of the periodic table, including groups and periods. We're going to be using rules and patterns to construct our own periodic table. We're going to identify how certain things like atomic number, mass, and electronic structure contribute to the organization of the periodic table. And then finally, we're going to define some things like group and period. So we are actually going to begin today at the very, very back of the study guide. This is page 18. If you're asking, why isn't it at the front? I don't know. I didn't put it at the front. Deal with it. Page 18, you're going to start by doing this front portion here. The materials you're going to need are at the front of the room. There are sets of periodic table blocks. They're little pieces of paper that you're going to cut out. Each set has 3 pieces of paper. I'm going to say that again. Each set has 3 pieces of paper. So make sure that each pair or group of 3, whatever you choose to work in, has a full set. You're going to cut out those element blocks, and then you're going to follow these steps. Step 1 says, without using a periodic table, so obviously don't look, it says to arrange the elements in rows and columns in a logical manner, meaning whatever makes sense to you. 2 says to write down the rules. What was the logic behind the way you made it the way you did? And then 3 says to check. I'm obviously not there, so I can't check it. So don't worry about that part. But what we want to do right now is we want to build our own periodic table, excuse me, according to our rules. I'm going to let the sub pause the video here. You're going to go and get the materials that you need. That should be a set of element blocks with scissors. You're going to cut them out and you're going to follow the instructions. When you are done, stop. Don't move on to the rest. Just stop. Okay. Sub will pause the video now. Okay. So however you decided to build it, I've seen lots of different ideas and lots of different methods and rules and logic, and they're all valid. It was just an activity to see what you came up with. What we're going to try now, you're going to jumble it up again, and you're going to build a new periodic table, but this time you are going to follow these rules. Let me move my face out of the way. 1, you're going to order the atomic mass so that it increases from left to right and top to bottom. So in the top left of your periodic table should be the lightest elements, and in the bottom right should be the heaviest. The other rule I'd like you to follow is I would like you to group elements with the same number of valence electrons in the same column. I'll say that one more time. Group elements with the same number of valence electrons in the same column. Okay. Again, I'm going to let the sub pause the video here. I'm going to let you get to work. When everybody's done, the sub will play the video. Ready, set, go. Okay. Now that you've done that, hopefully you saw some interesting things. One, you should have seen that it fits nicely together. You also should have seen that as you made it, there was a gap, a little hole where an element should be, but didn't exist. And hopefully that's where you put your little mystery element. What I found is when we kind of use random rules like alphabetical or even rules like increasing number, we don't really get the chance to predict where missing elements should be. But if we follow these rules, then it turns out that that's kind of what happens. Natural gaps tend to form. And that's exactly the process that really the main contributor to the periodic table as we know it. That's the process that he used. His name was Dmitry Mendeleev. And that was kind of the rules he used. He used increasing atomic, technically mass, but we use atomic number. But he also grouped elements with similar properties in the same column. And what he found was that there were gaps in his periodic table of elements that had not yet been discovered. And later they would be discovered. And they fit in his periodic table exactly where he predicted they would be. And they had properties that he predicted they would have because he knew that elements in the same column should have similar properties. So what I want to do now is answer these questions on page 18. Number 1 says, on which side of the chart do you find metallic elements? Tell your partner really quick. Hopefully you said the left side. The left side mostly has all the metals. Number 2 says, what happens to mass and also atomic size of atoms as you move down a column? Tell your partner. Hopefully you said it gets bigger. Number 3 says, what might account for the trend described in the previous example? Well, it seems maybe that the more stuff there is in an atom, then the bigger it tends to be, the more space it tends to take up. Number 4 says elements in the same group or family, which we know now means column, usually share similar chemical properties. Find the element sodium, and it says list the symbols for 4 other elements in the same family. So we can have a number of other elements. We can have lithium, we could have potassium, we could have rubidium, we could have cesium, or we could have another element. But those are the 4 I would pick. 5 says look at the chemical properties of the elements in the group in question 4. So sodium, lithium, rubidium, potassium, cesium. Look at the properties of these elements. Are they similar or different? Hopefully you see that they're very similar. Number 6 says the word periodic refers to the rows of elements whose properties repeat themselves. That's why we call it the periodic table. Periodic means repetitive. So as we work our way across a row, we have different chemical elements with different properties. And then when we start back on a new row, those properties repeat themselves. That's why it's called periodic table. It says boron and aluminum are members of the same group. How are they similar? You can look at those and then write that down. Oh, sorry. Number 8 says the blank card, this is the cool part, the blank card represents one of 3 undiscovered elements, which Mendeleev, the main creator of the periodic table as we know it, that blank card represents a gap that he left in his chart because he thought that a different element belonged there that had not been discovered yet. He was actually able to predict the properties of this unknown element by looking at the properties of the elements above and below it. That's aluminum and indium. Using the properties of these 2 elements, it says to predict the following about the unknown element. We should be able to predict its mass. Maybe not an exact number, but at least a range of values that it should be in between. We should be able to predict if it's a metal or a non-metal. We should be able to predict what color it'll be, and we should be able to predict if it's hard or soft. So I want you to talk to your partner and fill in these 4 blanks. The sub can pause the video here, give you a minute or 2, and then unpause when you're ready. Okay, let's take a look at this mystery element and see if your predictions are correct. This mystery element's name is gallium. It has an atomic mass of 70. It is a metal. It has a silvery, almost blue hint to it. Relatively soft, and it's actually quite rare. It does have 3 valence electrons, which is why it's in the column that it is. And it has an atomic radius of 135 picometers. I have this video here that I'll play for you, but I actually have a good sample of gallium, and it's kind of a fun little metal to play with. It's got some unique properties. So the day that I come back, I promise I will show you my gallium, and we'll get to see it. But I'll show you this video for now.
Here I have some gallium, and at room temperature, it's completely solid. However, it has a super low melting point of only about 30 C or 86 Fahrenheit. So if I put it into a bowl of hot water, it should completely liquefy. It all eventually melted, and what I have now kind of looks like mercury. Unlike mercury, though, it's not nearly as toxic, and it's much safer to hold in my hand. However, it is a lot messier, and it tends to stick to things and leave an annoying residue.
He's definitely right about that. I tend not to hold it for that very reason. It's very sticky, unlike mercury. But like you said, you don't want to touch mercury. Mercury can actually be toxic when it seeps through your skin. Gallium's not really toxic through your skin, but it is toxic if you ingest it. So don't eat gallium. Okay, back on that page, there's one other thing we have to fill in, and that's number 9 down here. It says francium is a radioactive element that appears directly below cesium in the periodic table. And it says to make predictions for the following properties of francium. So the same 4 things you predicted about gallium, predict about francium this time. Again, it's directly below cesium. So the sub will pause the video, give you a minute or 2, and then play it when you're ready. Okay, let's take a look at francium. Francium has an atomic mass of 223. I put metal and silver gray, but I put them in asterisks, and I'll explain why in a minute. It does have one valence electron. Francium is extremely radioactive, which means that the actual identity francium does not last very long. It tends to decay into other elements very fast. It's even more rare than gallium, and it has a pretty large atomic radius. I put these little asterisks here because you're probably looking at this picture and you're thinking, that doesn't look like a metal. That's definitely not silver gray. And you'd be right. This is a rock. This is not a pure sample of francium. Rather, this rock has francium in it. How much francium? Not a lot. In fact, the reason that I put asterisks here is, to date, we have never accumulated a large enough sample of francium to actually know for sure if it has metal properties, if it is silver gray. We don't know. It's so rare and doesn't last very long that we can't tell if those properties are real or not. We just predict that it's like that because of the trends and the patterns that we know exist in the periodic table. So that's kind of a weird thing about this francium metal, but yeah, it's in this rock. It's not the rock itself. All right, let's move on then. We're going to go to page 1, and we're going to include a little bit of notes here. The first thing I want to point out on this page is often when you see a periodic table, you kind of see this nice little structure up here, and then you see these 2 rows down at the bottom that are totally detached. I don't know if you've ever wondered why those rows are down there. I'm going to tell you why, but in reality, those rows don't actually belong there. In reality, those rows, which are called the actinides and the lanthanides, those rows actually belong right here and right here, in between these 2 elements and these 2 elements. So this row here, which we call the lanthanides, belongs right there after the element lanthanum. And this element here, or sorry, this row here belongs right here after the element actinium. So if we had an accurate periodic table, it would look like this. Now you can probably guess why we have chosen to remove these 2 columns and place them kind of underneath. And that's simply because we like to print things and put them on posters. And this isn't a super friendly poster, but this looks better on paper and printing wise. So that's the only reason we do it. So I just wanted you to know that these columns are not like separate or mysterious elements. They're part of the periodic table, just like the rest. They have a place, and it's right here. All right, let's move on and let's answer these questions down here. And this, I believe, will be the last thing we do today. Number 1 says on the periodic table, period refers to, what do you think? Does it refer to a column or a row? 3, 2, I'm tired, sorry. 3, 2, 1. A period refers to a row. A period refers to a row. And the reason, like I said before, we call it a period is because every time you go down a row and then start again in a new row, you repeat the pattern of chemical properties that you saw before. Number 2 says, across a period from left to right, identify a trend in atomic mass. Hopefully you can see from the periodic table you built, but also from the actual periodic table, that atomic mass increases as you go from left to right across the period. Number 3 says on the periodic table, groups refers to, well, it must refer to columns. Columns of elements are called groups. Other times they are actually called families. So you might want to write that down as well. So anytime we say group or family, we are referring to a column of elements. Elements in the same, and then you're going to fill in this blank. Elements in the same group or period have similar chemical properties. The correct answer there is group. Elements in the same group have similar properties. Elements in the same period have very different properties, but when you start a new period, you repeat the pattern. And the pattern is there because elements in the same column or group have similar chemical properties. Last one here says elements in the same group or period have the same number of valence electrons. And hopefully you saw from building your own that it's the group. Elements in the same group have the same number of valence electrons, the same column. And we're going to see that it's not a coincidence that elements in the same group have the same number of valence electrons and also have similar chemical properties. That is not a coincidence. And we're going to see why as we move forward. Hey, let's try just a little bit of practice to wrap things up. Find an element with the same number of valence electrons as aluminum. I'll give you 5 seconds. Okay, could have said a number of things. You could have said boron, you could have said gallium or indium, anything in the same column as aluminum. This one says find an element with properties similar to bromine. 5 seconds. Any of those elements in column 17. So fluorine, chlorine, iodine, any of those have similar properties to bromine. Not identical, but similar. Find an element in the same family as barium. 5 seconds. Okay, barium, I believe, is in column 2, so you could have chosen magnesium or beryllium or calcium. Those are all in the same family because family means column. Okay, lastly, number 6 on that page says write the pattern for valence electrons in the periodic table above. So what I want you to do here is we know that elements in the same column have the same number of valence electrons. That's well established, but we should be able to do a little bit better, right? For example, this first row, or sorry, not row, first column here, all of these elements have the same number of valence electrons, but you should be able to tell how many they have based on the periodic table that you made. That's 1. Every element in this column has 1 valence electron. Every element in this column has 2 valence electrons. These elements here in the middle, these are called the transition metals. We didn't actually deal with them, so we're not sure yet on a pattern there, so we're going to skip those. We're going to move all the way over here to this group. This is technically group 13, but it's sometimes called 3A. Can you guess how many valence electrons that these elements have? It's 3. This group here has 4, starting with carbon. This group here, starting with nitrogen, has 5. This group here, starting with oxygen, has 6. This group here, starting with fluorine, has 7. And this group here, starting with helium, has 8. Now, I do want to make a note of one exception. When you made your periodic table, you likely didn't have helium all the way over here. You likely had it over here, right above beryllium, because helium has 2 valence electrons. But what we're going to find is that helium actually doesn't have properties similar to everything else in this group 2. Helium is not like, excuse me, beryllium or magnesium or calcium. In fact, helium is a lot more like neon and argon and krypton and xenon. And that's why it's placed over here. And we're going to learn a little bit more about helium and why exactly it's over there. But for now, it'll suffice to say that all these elements have similar properties. That's why they're in the same column. Every element in this column has 8 valence electrons, except for helium. Helium has 2. And we'll see why that exception exists a little bit later. Okay, I believe that is all I have for you today. Good work. Thank you for participating. As far as what to do with the elements and the paper you cut out, I don't have any really like good storage for you to put them in. No, actually, I do. Let's do this. On the bookshelf, I think middle top row, I have cups, and some of those cups they're clear and they're plastic. Some of them have stuff in them already, but I think I have a nice set of empty cups. If you could kind of keep your set of elements together and just put those element paper tiles in an empty cup and then just put it on the bookshelf, that would be really, really helpful. I appreciate you doing that for me. And if it doesn't work out, it's not a huge deal. Okay, I think that'll do it for today. Thanks so much. Hopefully I'll see you guys soon.